Okay, here is another example. We would like to solve the fourth order ODE minus 3 times y triple prime minus 2y double prime plus 2y prime plus 12y is 0. So clearly, this is a fourth order ODE. Where the differential operator of degree 4 in D is clearly has this form, okay? And characteristic equation is this one, or explicitly lambda 4 minus 3 lambda cube minus 2 lambda squared plus 2 lambda plus 12 is 0. Okay. As you remember, we propose a solution of this form. This is the proposed solution. And we find the possible lambda values, which makes this function indeed a solution. And lambda values are the roots of this characteristic equation of fourth order form. Now, if the order of, or if the degree of the polynomial, the characteristic polynomial is a large one, of course, finding its roots may be difficult. In the second order case, remember, or in the second, for a second degree polynomial equation, remember we have standard formulas to write down the two roots explicitly. For cubic equation, again, although they are a little bit complicated, it is possible to express all the three roots by formulas, okay? By analytical formulas. And for the fourth degree polynomial, it is also possible to express all four roots, okay, by some formulas, but they are very complicated, okay? But in this case, because this is a course on differential equation, it is not a course which tries to find the roots of algebraic equations. So it is not difficult to see that the left-hand side assumes somehow that we find all the roots. So we give it's the factorized form of the characteristic equation or characteristic polynomial may be given, like lambda minus 2, lambda minus 3, and lambda plus 1 squared plus 1 is 0. So this is the factorized form. Of the characteristic polynomial L of lambda. Okay, be careful. Okay. You may verify that this is indeed the given for the product gives us the characteristic polynomial. Okay, so as you see from the factorized form that equating the first factor to 0, we see that, say, lambda 1 is 2, is a root of the characteristic polynomial or characteristic equation, sorry. Lambda 2, 3 corresponding to this factor we see that a second root of the characteristic equation is 3. And these are real and distinct roots, but the remaining 2 roots are complex. As you see, lambda plus 1 squared plus 1. When the last factor is equated to 0, we have lambda plus 1 squared, which is minus 1. And therefore, the third and the fourth root of the characteristic equation is a pair of complex roots with minus 1, with real part minus 1, and imaginary part 1. Good? So these are real and distinct roots. So case 1, the statement in case 1 tells us that. So the first solution, obviously, as we propose a solution like that, and since lambda satisfies the characteristic equation, the corresponding exponential function with lambda 1, 2, t is indeed a solution. Similarly, when lambda is 3, the exponential function with lambda equal to 3 is a solution again. And case 2 suggests that the third solution is e to power exponent of the exponential factor is the real part of the complex root. So minus t times cos bt. So look, a is minus 1, b is 1 in this complex, in this pair of 2 complex roots. So we have cos t, and fourth solution is e to power minus t times sine t. As you see, b is 1. Therefore, all 4 solutions have been obtained. They are linearly independent. They form a fundamental set of solutions. So general solution of our 4th order linear homogeneous ODE with constant coefficient is the combination of these 4 functions, where C1, C2, C3, and C4 are arbitrary constants. E to power minus t, C3 cos t, C4 sine t is the general solution. Right? Please be careful when we say solve an equation. Okay? We mean find the general solution. Okay? So we find the general solution having C1, C2, C3, C4 are arbitrary constants. C4. In the sense that for any values of these constants, the function in this form describes a solution of our equation for any choice of values of C1, C2, C4. Okay? So another remark is that if the factorized form of L of d or L of lambda is known, then it is not difficult to form all solutions. But as the degree of the characteristic polynomial increases, the labor involved in finding the roots increases accordingly, and therefore may be very difficult to find all the roots exactly. Okay, now it remains one more cases. As we stated at the beginning of this lecture, a polynomial equation has roots which are real and distinct, which are complex, or which are repeated. Now, Let's consider the third case where the characteristic equation has repeated real roots, but the result we get will be valid for the repeated complex roots as well. Let us state the result first for repeated real roots. Okay, say case 3. Repeated roots. Okay, so if the characteristic equation L of lambda equal to 0 has a real root, say again, lambda 1 of multiplicity k. K is a positive integer which may be at most n, yes? Because we have totally n roots, and multiplicity of a repeated root will be at most 10, which means that the root lambda 1, whatever it is, lambda 1 repeats k times. In other words, this is a repeated root. It repeats k times. So it represents k roots of the characteristic equation. Remaining roots, it remains n minus k roots. Okay? So we have to find k linearly independent solutions corresponding to this root. So clearly, e to power lambda 1t is a solution. But what are the others? We have to express k solutions corresponding to this root. So this theorem, in case 2, there is a theorem which tells us that multiplicity k smaller than n, then, let us complete our sentence, then the k solutions corresponding to this root are given by e to power lambda 1t, which is clearly a solution because lambda 1 is a root of characteristic equation. E to power lambda 1t is clearly a solution. The others have the form t times e to power lambda 1t, t squared times e to power lambda 1t, and finally t to power k minus 1 e to power lambda 1t. So totally k solutions. Hence the corresponding part. Corresponding part of the general solution is of the form C1. So each contains e to power lambda 1t. So we have C1, C2 times t, C3t squared ck t to power k minus 1 times e to power lambda 1 t is the corresponding part, or is the solution corresponding to lambda 1, which is a root with multiplicity k. So k independent solutions are given. Please be careful. In the case of a complex root, we obtain a solution which is an exponentially weighted circular function in the case of a complex root. Now we have a solution which is a polynomial weighted exponential function. Okay? So in other words, we have an exponential multiplied by a polynomial in t of degree k minus 1, corresponding to k tuples, or corresponding to a root with multiplicity k. Good? Now, there are several ways of proving this result. I prefer to use the following proof. We give some outlines, basic outlines, to see why the solutions are given in this way. Okay. So recall, with y proposed solution e to power lambda t, what we get? We get L of d, and do not forget, we are interested in this differential equation, which is homogeneous, linear of order n with constant coefficients. So substitution of that into our equation, L of dy, the left-hand side of our equation, becomes e to power lambda t times L of lambda. Good? We prove it several times. When this is substituted into the equation, the left-hand side becomes this. And when we equate this 0, okay, and if we find a root of characteristic polynomial, okay, then this result becomes 0 for that lambda, so making this function as a solution. Now, we get this where, remember, L of lambda in this case contains a factor. Look, what is our assumption? The number lambda 1 is a root. So L of lambda contains this factor. However, since it repeats k times, we must have lambda minus lambda 1 to power k as a factor in the characteristic polynomial. Okay? So L of lambda, so what? So look, this equation, L of d, when e to power lambda t is suggested as a solution and substitute into the equation, we get this result, e to power lambda t, L of lambda. Okay? And this e to power lambda t, L of lambda contains this factor lambda minus lambda 1 to power k times, look, this is a polynomial of degree k in lambda, and recall that L of lambda is a polynomial of degree n, so it remains a polynomial of degree n minus k in this decomposition. Let's say again t. T is a polynomial in lambda of degree n minus k. Okay? Lambda, yes, of degree n minus k. So let's finish our sentence, complete our sentence where t n minus k of lambda is a polynomial in lambda of degree n minus k. Okay, such that, please be careful, lambda 1, the specific first root, is not a root of this polynomial. Because if it is a root, then the multiplicity of lambda 1 will be k plus 1. Okay, so such that t n minus k lambda 1 is not equal to 0. Good? Now, with this main result, clearly first, we see that when lambda is lambda 1, good, this equation is 0. When lambda, because k is not 0, it is at least 2, okay? So when lambda is lambda 1, clearly L of the e to power lambda 1t is 0. Look, replace lambda by lambda 1. So the right-hand side becomes 0, and L of the e to power lambda t becomes 0, implying that the first solution is e to power lambda 1 t, as suggested. Second, now look, I'm going to use the following technique here. Lambda is a parameter. So the proposed solution e to power lambda t, okay, may be regarded as a function of two variables in lambda and t. And therefore, I can take the partial derivative of this function with respect to lambda as well. Good. Now, it is possible to regard e to power lambda t, the proposed solution, as a function of two variables, lambda and t. Good. In this case, so, for example, we can talk about the partial derivative of e to power lambda t with respect to lambda as t times e to power lambda t. And as you remember, in partial differentiation, the order of partial differentiation is immaterial. So you can take the partial derivative of a function first with respect to lambda and then with respect to t. Of course, under some conditions, but in this case, we have a very nice function. So the order of differentiation is immaterial. So you can interchange the order of partial derivative with respect to t and with respect to lambda without any problem. Okay? So this is the case. And let us denote this result as asterisk. Okay? So this is the case, and recall also that, the order of partial differentiation may be interchanged. Now, so look at the equation in asterisks. It is clearly e to power lambda t times L of lambda. So it is a function of lambda and t. Good? So taking the partial derivative of both sides of asterisks with respect to lambda, we first d lambda L of t e to power lambda t. Good? Del lambda e to power lambda t times, look at that, the right hand side is lambda minus lambda 1 to power k t n minus k lambda n minus first. This is the polynomial in lambda of degree n minus k, and the product of three functions. Look, the second factor and the third factor are functions of lambda only, but the first factor depends also on t. So I'm going to take partial derivative of both sides with respect to lambda, and keeping in mind that, look, what is L of t? L of t shows derivatives with respect to t. And since the order of partial differentiation may be interchanged, the left-hand side, where the left-hand side, this stands for the abbreviation of left-hand side, may be taken as look, L of t del lambda e to power lambda t on interchanging the order of partial differentiation. That L of t implies derivative with respect to t. Okay? So derivatives with respect to t and derivative with respect to lambda may be interchanged. So usually left-hand side, first look, L of t e to power lambda t. We are going to take the derivative of e to power lambda t with respect to t up to order n. And then we take the partial derivative of the result with respect to lambda. But with this formula, first we take the partial derivative of e to power lambda t with respect to lambda, and then take the derivative of the result with respect to t up to order n. And this is these operations are equivalent since the order of partial differentiation may be interchanged. Okay, so look, because e to power lambda t has t as this, t times e to power lambda t. Good, we get this result. On the other hand, taking partial derivative of the right-hand side, we have to take partial derivative of the product. So what is the partial derivative of the first term with respect to lambda? T times e to power lambda t, good, times this, lambda minus lambda 1 to power k, times t n minus k lambda. Now, the partial derivative of the second factor using usual product rule differentiation, we have e to power lambda t, k times lambda minus lambda 1 to power k minus 1 times t n minus k lambda, plus there is one more term. What is it? E to power lambda t, lambda minus lambda 1 to power k times the derivative of t with respect to lambda, which is the ordinary derivative. So I can use prime notation without any trouble. I take the derivative of this n minus k degree polynomial with respect to lambda. Okay? Say double asterisk. Now we get this result on taking partial derivative of both. This is an identity. So we take the partial derivative of both sides with respect to lambda and use the fact that the partial differentiation may be interchanged, and we get this result. Now, what happens when lambda is lambda 1? Good? Now, when we get clearly L of t, t e to power lambda t, left-hand side, okay? Put lambda equal to lambda 1. What about the first term? K is a number which is larger than 2, an integer, positive integer. So when lambda is lambda 1, because of this factor, yes, the first term is 0. Because k is larger than 2 or equal to 2, yes, there is a factor here, lambda minus lambda 1. So which is 0 again when lambda is lambda 1. And this term, this factor is also 0, making the last term 0. So what is the result? We get L lambda equal to 0. Because since k is at least 2. So what is the meaning of that? What is the meaning of this relation? Which implies that. Look, do not forget, we have always this equation. And we are looking for a function y upon substitution of which gives 0 to say that it is a solution, to conclude that it is a solution. So we see that. Look, if we substitute t times e to power lambda t for y, the result is 0. So t to power e to power lambda t is a solution, which implies that, so which is a second solution when lambda is lambda 1, which implies that y1 we have already write here y1. So let us denote it this y2 t times e to power lambda t. So do you understand? Look, I substitute t e to power lambda t for y, and we see that the equation gives us 0, which means that t e to power lambda t stands for a solution. And this is a second solution because we have already a solution, e to power lambda 1t. So we get a second solution. Lambda 1, yes, when lambda is lambda 1. Good? And continuing in this way, if k, this is true when k is larger than or equal to 2. If k is larger than 3, okay, taking the derivative, similarly, taking the derivative of the statement of the equation in a double asterisk with respect to lambda once more, okay, again using the interchange of partial derivatives, the left-hand side, taking the derivative of the result with respect to lambda once more, we get t squared e to power lambda t here. And if k is larger than 3, the right-hand side is still 0 when lambda is replaced by lambda 1, implying that t squared e to power lambda t is 0. Hence, continuing in this way, we get the required result, okay? So, okay. Let's write, if you want, let's write the result we obtained for completeness. Okay. So if k is larger than or equal to 3, okay? Now, differentiation of double asterisk or the equation in double asterisk once more with respect to lambda, okay? And then setting lambda equal to lambda 1, we get similarly L of t, taking the derivative with respect to lambda, left-hand side becomes t squared e to power lambda t, and setting this, lambda is lambda 1, taking the partial derivative of the right-hand side. This is a little bit long, some long calculations, okay, but straightforward. So we'll see that the right-hand side is 0 when k is larger than 3. So, which implies that t squared e to power lambda 1t is 0, which implies a third solution. Good. And continuing in this way, continuing in this way, we find out that ykt is t to power k minus 1 e to power lambda 1 t, which completes the proof of the statement in case 3. which completes the proof of the claim in case 3. Okay? Here is a result. Here is a remark, important remark. This result or the way of generating k solutions corresponding to a repeated root. Okay? So this result in case 3 is true also for complex repeated roots. For example, if lambda a plus or minus ib, okay, is a pair of complex root. So if lambda is a double root, with k is equal to 2, okay, then look, we have a pair of complex roots which represents 2 roots of the characteristic equation. It is these both are double roots, so they represent totally 4 roots of the characteristic equations. So we have to generate 4 solutions corresponding to such a double root, which is a complex pair. Good? Then y1 of t, what we know that e to power at cos bt is a solution. y2 e to power at sin bt is a solution. And now case 3 tells us that because this root is a double root, multiplying t, the first solution, multiplying by t, the first solution, we get another solution. So, which is the third solution, is t times e to power at cos bt. And it is true for this as well. So multiplying by t e to power at sin bt is again a solution. So we get all 4 solutions corresponding to a complex root which is repeated 2 times, or a complex pair of 2 roots which repeats 2 times with multiplicity 2. Good? So now we generate, as long as we find the solutions, we find the roots of the characteristic equation, okay, as real distinct roots, or real repeated roots, or complex roots, or complex repeated roots, we generate the corresponding solutions without any trouble. And in any case, we see that the solutions we generate looking at case 1, following the statements of case 1, case 2, and case 3, are all functions in terms of elementary functions. To be specific, a solution of a homogeneous ODE, homogeneous linear ODE with constant coefficients, may be a combination of exponentials, powers and a trigonometric function, basic trigonometric function. Yes? So let's write it as a first remark. So we have shown that remark, important remark. We have shown that all solutions of a linear homogeneous ODE with constant coefficients in this L of dy, where we use this abbreviated form, are combination of functions of the form or of the type, all elementary function, e to power lambda t. Yes? Where lambda is some real number or sin bt basic trigonometric functions or circular functions where again for b may be any real number here, or this e to x t to power n, where n 1, 2 is a monomial, is an integer. Good? But let's say k, in order not to confuse with the order of the differential equation, where k is this. So the solutions of such an equation are all expressible in terms of elementary functions, okay? Which are combinations of exponentials, circular functions, and monomial in the general situation. And this is a finite combination. Good? Another remark is that remember the characteristic equation we obtained. Characteristic equation, okay? L of lambda equal to 0. We obtain it by interchanging d with a parameter lambda. So we get a polynomial equation, a polynomial of degree n in lambda, okay? This characteristic equation is nothing but equivalent to the characteristic equation we find as, remember the systems, this is equivalent to, if you think about the system representation of an nth order ODE, okay? Remember, when we have a system, we have a coefficient matrix of the system. This is identity matrix of the order, of the same order as A. So determinant of this matrix A minus lambda I gives us the characteristic polynomial, okay? And equated to 0, we get the characteristic equation. So it is equivalent to the characteristic equation obtained by using this determinant. So to illustrate the procedure, let us use the second order case for simplicity. To illustrate this, so let's say for simplicity, let us consider the second order case for illustration. Look, so consider this. Y double prime plus A1 y prime plus A2y is 0. This is L of D y. Okay? So clearly, L of lambda is lambda squared plus A1 lambda plus A2. Now, the system representation of y double prime plus A1 y prime plus A2 y. I'm not going into the details. We did it several times. Is this the system representation is that x prime ax, okay, where the coefficient matrix is nothing but 0, 1, and minus A2 minus A1, right? So system representation of a second order ODE, homogeneous ODE is that. And therefore recall that then the characteristic equation or characteristic polynomial is this. A minus lambda times identity, that is determinant of this matrix 0 plus 1 plus lambda, or minus lambda, sorry, and 1 minus A2 minus A1 minus lambda, okay? This is A minus lambda I. Look, A minus lambda identity is this matrix minus lambda 1 minus A 2 minus A1 minus lambda, okay? Or let's write explicitly 0, 1 minus A2 minus A1 minus lambda times identity. Good. So it gives this one. Therefore, if you calculate the determinant, you see that we have lambda squared, or lambda times A1 plus lambda plus A2, which is lambda squared plus A1 lambda plus A2. Good. So this is the characteristic polynomial of the matrix A minus lambda identity, as you see, which is nothing but L of lambda, which is obtained more directly. Good. So to conclude, let us give a more general example. Now, we are in a position to solve any homogeneous linear ODE with constant coefficients, provided that the roots of the characteristic polynomial are all known, of any type, real, complex, repeated, etc. Yes? And look, if the characteristic polynomial, or accordingly the differential operator L of D is given in its factorized form, it is not difficult to find the roots of the characteristic equation. So in order not to deal with the boring problem of finding the roots of a polynomial equation, let us assume that the factorized form of the differential operator is given or is known. So let us consider such an example. Let's form, here is a general example. Solve the homogeneous ODE where L of D, look, is given as, look, I know its factorized form, assume D minus 1/2, okay? D plus 3 squared, then D plus 4 D squared plus 4 squared D minus 1 over E, or E, say Euler number, squared plus 2. Good. So where L of D is that, written in factorized form. Okay? So first of all, what is the order of this ODE? Look, it is the degree of L of D. So what is the degree of L of D? 3, 4, 5, 6. Okay, plus 4, 10, plus 2, 12. Okay, so the order of this ODE, 12. In fact, this is a, if it is not given in a factorized form, this is given as an ODE like Y12. Good. Some number Y11. A(n minus 1 y prime, a(n y) equal to 0. Okay? It will be given in that way. This is 12. Yes, this is n minus 1, 11. This is 12. Good. It will be given in that form. Okay? So thanks that somebody find its factors, find the roots and factorize our differential operator. So next, characteristic equation. As you remember, to solve such an ODE of order 12, we need to find the roots of the characteristic polynomial. So L of lambda, what it is, look, lambda cube, lambda minus 1/2, lambda, and it is obtained characteristic polynomial is obtained simply replacing d by lambda, which is a parameter to be determined, plus 3 squared, lambda squared plus 4 squared, and lambda minus e squared plus 2 this is the characteristic equation, should be equated to 0. Good? So, as you see, if lambda is 0, characteristic equation is satisfied. So lambda 0 is a root, but we have lambda cube, which means that 0, this root repeats 3 times. So it represents 1, 2, 3 roots. Good? Therefore, what is the solution for lambda? Do not forget, we propose a solution of this type. So when lambda is 0, this becomes a constant. Okay? So from which we generate which solutions? 1, it is a triple root, so t times 1, or let's say e to power 0t is a solution. T times e to power 0t is a solution, and tk minus 1k is 3 in this case. T squared e to power 0t are 3 solutions corresponding this root at 0, which repeats 3 times. Okay? So we generate y1 is 1, y2 is t, y3 is t squared. Okay? So 3 solutions corresponding to the root at 1 are given in this way. What else? Look, the second factor, lambda minus 1/2, when this factor is equated to 0, the left-hand side becomes 0, implying lambda 4, say, 1/2 is a root of the characteristic polynomial. So this is a distinct root. Okay? There is or a single root, not a multiple root. This is a single root which suggests the fourth solution, e to power 1/2 t, when lambda is 1/2. Okay? And lambda plus 3, look at that, lambda plus 3 suggests that lambda 5 is minus 3. But we have one more factor, lambda plus 3 times lambda plus 3. So this root repeats 2 times. It is a double root. So it represents 2 roots of the characteristic equation. Minus 3 is a double root, which this is the case 3. So the corresponding 2 solutions are e to power minus 3t, when lambda is minus 3. But also t times e to power minus 3t is the solution. Good? And for this factor, lambda squared plus 4, look at that, what we have. Lambda squared plus 4 is 0, means lambda squared is minus 4. So lambda is either 2i or minus 2i. So we have lambda plus or minus 2i. Okay? And which are double roots. Look, we have squared, so this factor, okay, repeats 2 times, which implies that the 2 roots are double roots, and they represent totally 4 roots. Okay, so lambda 7 8, 9, and 10 are roots like that. Therefore, the corresponding 4 solutions, y7 is, this is a root where exponential part is 0, a real part of the root is 0, so exponential factor, recall the case 2, becomes unity. So we have polynomial, trigonometric factor, cosine 2t, y8 is sine 2t. Good. We just use the imaginary part to find the 2 solutions. And since it is a double root, because of that, okay, we see that t times cos 2t, and finally t times sine 2t are also solutions corresponding to this root, which is a double root. Okay? Now, finally, we have this factor. So, that factor suggests that, look, lambda minus e is the Euler number, which is something 2 times 7, 1, and so on. Squared must be minus 2. Therefore, lambda minus e is plus or minus square root of 2, I times the square root of 2. And lambda represents 2 roots, say 11 and 12 roots of the characteristic equation are e plus or minus I radical 2. So the corresponding solutions are y11t, real part is e, so e to power et. Okay, e is a number. Times cos square root of 2t. Good. And y12t is e to power et times sine square root of 2t. So we get all 12 roots of our differential equation, which is of order y12t sine. No, it is not a repeated root. It is a single root. Okay, but we have 2 roots. This complex root is repeated because we have 2 factors like that. Lambda square 4, one more lambda square plus 4. So the roots of this factor repeats, but these are both single roots. Okay, so this root e plus or minus I radical 2 is a complex pair of 2 single roots. Okay, so we have, please check the number of solutions by using the order of the differential equation. Precisely, the number of independent solutions will be equal to the order of differential equation. So we get 12 solutions for a 12th order homogeneous differential equation. And of course, taking the combination of these 12 solutions, we get the general solution. Okay? So general solution is something like that. I'm not going to write it in full form. General solution is the combination like this. C1 C1 plus C2t plus C3t squared plus C4 e to power 1/2 t dot dot dot. Finally, C12 e to power et sine radical 2 t, the combination of all 12 solutions.